In the 13th century, Nachmanides, known as the Ramban, wrote a dense, highly influential commentary on Exodus 25, the biblical passage detailing the Ark of the Covenant. In the centuries that followed, dozens of scholars wrote their own works directly responding to his exegesis. To analyze how these subsequent texts relate to the original, digital humanists typically rely on keyword matching or n-gram fingerprinting. But these word-level computational approaches fail to capture meaning. Two authors can describe the exact same concept using completely different vocabulary. Conversely, they can use identical terms to construct entirely separate theological arguments. To map the actual relationships between these ideas, we use a Python library called SimpleKG. It converts unstructured text into structured knowledge graphs, networks of discrete concepts and the specific relationships connecting them. By extracting the structure of the knowledge, we can compare historical texts based on the topology of their arguments, rather than just tallying their vocabulary. When we compare two extracted knowledge graphs, we categorize the concepts by color to establish a baseline. Green nodes are shared between both texts. Red nodes are unique to the later commentary. Blue nodes are unique to the original text. This network graph compares Ibn Shuayb's 14th century commentary against the Ramban. The data reveals a dense, integrated center of shared green nodes. He reproduces the core Kabbalistic framework, concepts like the Ark, cherubim, and throne of glory, connecting them using identical structural logic. We see a vastly different result mapping the commentary of Meirite Einayim. Instead of an integrated center, the network is sparsely distributed. The blue and red clusters remain isolated. The author uses Ramban's vocabulary, but fails to connect concepts into a shared relational structure. The disparity between these two visual maps is stark. The core technical question is how we algorithmically extract these precise nodes and edges from flowing medieval Hebrew prose and mathematically quantify the overlap. Visualizing these topological structures proves that scholars can utilize identical scriptural citations to engineer radically divergent intellectual networks. To measure this conceptual overlap, the system first isolates anchor concepts. These are direct citations of biblical verses, serving as fixed, unmoving reference points across all graphs, since all the authors are commenting on the same chapter. Everything else is classified as free concept. This category captures the specific interpretive vocabulary of the author, theological ideas, named figures, and physical objects. Aligning these free concepts across different manuscripts presents a major challenge. Direct character matching fails due to medieval spelling variations, prefix differences, and shifting vowel points. The compare-KG algorithm resolves this by scoring candidates through a hybrid mathematical formula. Semantic embedding accounts for 70%, mapping the underlying conceptual equivalence despite different phrasing. The remaining 30% acts as a failsafe, utilizing Jacquard similarity and English labels to anchor semantic fuzziness. This permissive scoring mechanism is only the first phase. It casts a wide net to generate highly probable alignment candidates. In the second phase, these candidates pass through a deterministic large language model verification gate. The model rigidly adjudicates each pair, stamping them with certain or highly likely confidence flags, and discarding the rest. This two-stage engine captures inevitable spelling variations of historical texts, while safely eliminating false semantic matches. Before we can align these concepts, the software must accurately extract the discrete nodes and directed edges from the unstructured manuscript. Processing a massive document through a single language model prompt leads to context dilution. The model distributes its attention across too many topics, generating broad summaries while hallucinating or missing fine-grained relationships. SimpleKG counters this by employing a sentence-based chunking strategy. The pipeline processes these overlapping chunks in parallel. It extracts an independent subgraph for every sentence, and then consolidates those discrete components into a unified document graph. Forcing the model to process the text at the microscopic level preserves the intricate relational arguments that a standard document-level summary obliterates. Historically, building text-to-graph pipelines required hard-coding specific linguistic rules for every new language or document type. SimpleKG solves this pipeline brittleness by using the DSPY framework. Instead of hard-coded rules, it utilizes declarative, pluggable signatures. The core pipeline is the NKG generator. It acts as a completely generic engine that knows nothing about the specific text it is reading. When we slot in the Ramban signature registry, we instantly program the language model with highly specific medieval domain expertise. These signatures instruct the model exactly what to look for, guiding it to identify scriptural references, abstract theological concepts, and Talmudic argumentation. DSPY strictly enforces these extractions into structured pydantic data models. This guarantees reproducible JSON outputs instead of conversational text. Decoupling the domain logic from the pipeline architecture makes automated extraction scalable across entirely different humanities disciplines without rewriting a single line of code. Returning to the generated network graphs allows us to synthesize our findings regarding the actual intellectual lineage of this corpus. We measure the structural spine of an author's argument using betweenness centrality, a metric that identifies which conceptual nodes act as critical bridges across the network. In the Ibn Shu'ib graph, high centrality nodes are almost entirely shared with the Ramban, perfectly aligning with the original theological framework. Extending outward from that shared center, we see the unique concepts Ibn Shu'ib added, expanding the Kabbalistic logic without breaking the framework. The pipeline reveals a drastically different reality in the Da'at Chakam Vatokan manuscript. Despite ostensibly commenting on the exact same passage, it yielded exactly 0 shared relational edges with the Ramban. This computational approach proves that texts presumed to belong to a single interpretive tradition can actually operate on entirely independent conceptual networks. The next stage of this methodology is multi-graph orchestration. By aggregating pairwise comparisons across dozens of texts, we generate massive similarity matrices to identify and cluster entirely new schools of thought. We are also deploying focus analysis tools to track how the centrality of specific ideas shifts and evolves across centuries of interpretation. To bridge this raw data back to humanists, the pipeline generates automated scholarly summaries, translating graph theory metrics into rigorous academic citations. By moving beyond word tallies and mapping the topology of arguments, we provide researchers with a reproducible, multidimensional lens to observe exactly how human knowledge structurally evolves over time.